Welcome back, scholars. It's time for our third and final look at how to solve various trig equations. This time, we'll focus on the use of multiple angles and inverse trig functions. Are you ready? Let's go. First up, you'll notice this equation introduces something a little different than our previous examples. Notice that while we are still solving for an angle, the argument or the input of the function is not simply x or theta, but is instead a multiple of theta. In other words, we are solving for 3 times theta this time. We'll approach this the same way that we do all algebraic equations. Let's get as close to isolating that unknown quantity as we can. I'll add 1 to both sides of the equation and then divide both sides by 2. Now we have cosine of 3 theta equals 1/2. I'll go ahead and find the angles where cosine is equal to 1/2. That will be pi over 3 and 5 pi over 3. Now, it's important to remember that these are technically angles that are 3 times larger than theta. So, to find theta, we'll perform one last algebra step here, which is to divide both sides of our solution equations by 3. Note that in this case, you'll probably find it useful to write dividing by 3 as multiplication by 1/3. These are 2 different ways of representing the same thing. So our solution equation should now read x equals pi over 9 and 5 pi over 9. One more thing to think about here. Consider how would we generalize these solutions? Normally, we would just simply add 2n pi radians. However, even in our general solution, we'll need to account for the angle multiple. In this case, since our multiple is 3, we'll divide our general solution by 3 as well. So instead of adding 2n pi radians, we'll add 2n pi over 3 radians to each solution equation. As always, it's a good idea to visualize these solutions using our graph, which is provided here on your screen and in your notes. The graph shows the solutions as x-intercepts since the right side of our equation is equal to 0. One more example. This time we'll look at how to use inverse functions to solve certain equations. Starting out, we have secant squared of x minus 2 times tangent of x equals 4. We'll need to rewrite the left-hand expression in terms of a single function, so I'll use a Pythagorean identity to substitute in for that secant squared x. Now I'll factor my trinomial into a pair of binomials. Then I'll set each factor equal to 0 and solve for x. In the final step on the left, in purple, note that I have tangent of x equals 3. Well, recall that the shape of the tangent function differs from that of cosine or sine. The range is not restricted to plus or minus 1 as it is with sine and cosine. In fact, the range is all real numbers. However, this angle is not one of our special right triangle angles. So we'll approximate this solution with our calculator or by simply writing it as the expression inverse tangent of 3, or arctangent of 3. In green, on the right, we're looking for the angle where tangent is equal to -1. I can write that equation using the inverse tangent function as x equals arctangent of -1, or inverse tangent of -1. In this case, due to the range of arctangent, my solution will be x equals negative pi over 4. We generalize each of our solutions using plus n pi, which is due to the period of the tangent function being pi radians. All right, that concludes our look at solving trig equations. We'll see you next time.